In this lecture, I will discuss the topic the field of sound waves and thereby explain the thermodynamics of solid. This is a problem which is mathematically similar to the one we discussed in last lecture, that is lecture number 27. But there are few conceptual differences between the two problems. So first I will explain the differences between the two problems. Then it will be easier for you to compare the two problems. For blackbody radiation, we talked about the wave inside a radiation cavity, which is nothing but electromagnetic wave. But for thermodynamics of a solid, we talked about wave of distortion of lattice, which is nothing but sound wave. For the case of a blackbody radiation, we considered the vibrational modes of electromagnetic field quanta, which are known as photons, whereas in the case of vibrational modes of solid, the energy quanta are known as phonos. In the case of blackbody radiation, the number of normal modes in the cavity is infinite, but in the case of the solid, the number of normal modes is finite, and for an n-particle solid, it is 3n. Okay, now we will consider the problem, the field of sound waves. We have, as in the case of blackbody radiation, two approaches. In the first approach, assume the system as a collection of harmonic oscillators, and the second approach, assume the system as an enclosed region containing a gas of sound quanta, which are known as phonons. Okay, now consider a solid of n atoms. Suppose the equilibrium positions of the atoms are denoted as xi bar, and this I can take values 1, 2, 3 up to 3n, because for each of the atom in three-dimensional space, we will have 3 coordinates. So for n atoms, there will be 3n coordinates. So the equilibrium coordinates are represented as xi bar, and at any particular instant of time t, the positions are represented as xi. So it is natural to define the displacement from equilibrium, and let it be theta I, and it is nothing but xi minus xi bar. Again, I can take values 1, 2, etc. up to 3n. Okay, so we are considering a solid of n atoms. These atoms are vibrating about their equilibrium position xi bar. At any particular instant of time t, the positions are xi, and the displacements from equilibrium positions are denoted as theta I. Okay, now we can define the kinetic energy. Kinetic energy is the sum of all the energies of all the degrees of freedom. Here you have 3n degrees of freedom. So kinetic energy is given by half m into sigma I equal to 1 to 3n xi dot square. But we have xi equal to theta I plus xi bar. When you take the derivative, xi bar dot is 0, because xi bar are the equilibrium positions that will not change with respect to time. So xi dot is nothing but theta I dot. Substituting here, you will get kinetic energy as half m into sigma I equal to 1 to 3n theta I dot square. Call this as equation number 1. Now we want to find the potential energy. Potential energy, of course, will be a function of all the position coordinates. So phi is a function of x1, x2, etc. x3n. We can represent it as phi of xi. We can expand the Taylor's potential energy as a Taylor series about the equilibrium point. So phi of xi equal to phi of xi bar plus the first derivative term sigma I dou phi by dou xi evaluated at equilibrium position xi equal to xi bar into xi minus xi bar plus the second derivative terms half into sigma I comma j dou square phi by dou xi dou xj evaluated at equilibrium position into xi minus xi bar xj minus xj bar plus the third order terms etc. This is the Taylor expansion of potential energy. Call this as equation number 2. Here this first term represents energy of solid when all the atoms are at rest at their mean position. We can call it as phi naught. Okay, this first term is the energy of the solid when all the atoms are at rest at their mean positions. Okay, let it be phi naught. The next set of terms, that is the first derivative terms, becomes 0 because this phi of xi, when you plot it against the variable xi, we can see that at the equilibrium position it will have a minimum, because equilibrium positions are defined as the position at which energy is a minimum. So at equilibrium position, the potential energy function will have a minimum. If you take the slope of the tangent at that point, that will be 0. And the slope is nothing but dou phi by dou xi. So dou phi by dou xi evaluated at xi equal to xi bar will be 0. So all the first order derivative terms will be 0. Now, the second order terms will be like half into sigma ij dou square phi by dou xj evaluated at equilibrium position. Xi minus xi bar is nothing but theta I. Xj minus xj bar is nothing but theta j. Plus the third order terms we will neglect because we are considering small displacements from the equilibrium position. So all the xi minus xi bar are very small. So we can neglect the third order terms onwards. So this is the final expression for potential energy. Once we have kinetic energy and potential energy, we can write Hamiltonian as the sum of kinetic energy and potential energy. So it is phi naught plus sigma I half m theta I dot square plus sigma I comma j alpha I j theta I theta j. This is equation number 3, where alpha ij is nothing but half into dou square phi by dou xi dou xj evaluated at equilibrium position. Okay. Now, from this expression, it is clear that the Hamiltonian contains cross terms, that is terms like theta 1, theta 2 or theta 2, theta 3 or theta 1, theta 3 like that. Okay. We can avoid these cross terms by performing a linear transformation from this set of coordinates theta I to a new set of coordinates qi, which are known as normal coordinates. And this procedure is explained in the textbook by Goldstein in the chapter small oscillations. So you can refer that. So by defining a set of normal coordinates, we can write the Hamiltonian as h is equal to phi naught plus sigma I half m into qi dot square plus omega I square qi square. What is the advantage of this notation? Here there is no cross terms. Okay, there are terms only like q1 square, q2 square, q3 square, not terms like q1, q2, q2, q3, etc. Okay, so Hamiltonian doesn't have any cross terms when you define a set of normal coordinates. Okay, now this omega I are the characteristic frequencies of normal modes of the system. And this I can take values 1, 2, 3, etc. up to 3n. Okay, so this from equation 5, this is equation number 5, we can say that energy of a solid over and above the minimum value phi naught. This is the minimum energy of the solid. So there is an additional term. So the energy of solid over and above the minimum value phi naught may be considered as arising from a set of 3n one-dimensional non-interacting harmonic oscillators whose characteristic frequencies omega I are determined by the interatomic interactions. We know that for a harmonic oscillator, one-dimensional harmonic oscillator, we have this expression, okay, half m xi dot square plus omega I square xi square. This is the equation for Hamiltonian of a harmonic oscillator. So exactly the same term is here, and this I can run from 1 to 3n. So this is actually the energy of 3n one-dimensional harmonic oscillators, non-interacting harmonic oscillators. Okay, so that is why this statement. Okay. Now we can derive the thermodynamics of solid in the same method as we did in the case of black body radiation. First we will define the energy eigenvalues of the Hamiltonian, and that is given by the minimum energy phi naught plus For the 3n one-dimensional harmonic oscillators, we have the energy eigenvalue sigma I equal to 1 to 3n ni plus half h cut omega I. These ni's are actually numbers and it can take values 0, 1, 2, etc. up to infinity. This omega I, this I can take values 1 to 3n. There are only 3n harmonic oscillators. Okay. Now, once we have the energy eigenvalue, we can define the grand partition function zeta, and it is given by sum over all states e raised to minus beta e minus alpha n. But by the same reason as in the case of black body radiation, alpha is 0 here, because alpha is the Lagrange multiplier which results from the constraint total number of particles is fixed. Here the particles are phonons and the number of phonons are indefinite. They are not fixed. So alpha is 0. We can define zeta as sigma e raised to minus beta e. Substitute for eta e from equation 6. You will get zeta equal to sigma ni equal to 0 to infinity e raised to minus beta phi naught minus beta into sigma I equal to 1 to 3n ni plus half h cut omega I. E raised to minus beta phi naught you can take outside. Sigma ni equal to 0 to infinity. Exponential of a sum is product of exponentials. Okay. So using that idea, we can write it as pi I equal to 1 to 3n e raised to minus beta ni plus half h cut omega I. Now we can reverse the order of taking summation and product. So we can write it as e raised to minus beta phi naught pi I equal to 1 to 3n sigma ni equal to 0 to infinity e raised to minus beta ni plus half h cut omega. When you put ni equal to 0, you will get e raised to minus beta half h cut omega I. When I put ni equal to 1, you will get e raised to minus 3 by 2 beta h cut omega I plus etc. This is actually the sum to infinity of a geometric progression with the first term e raised to minus beta half h cut omega I and common ratio e raised to minus beta h cut omega I by omega I. Okay. So we have the sum to infinity of a geometric progression as Sn equal to a by 1 minus r. Instead of a, you have e raised to minus half beta h cut omega I. Instead of r, you have e raised to minus beta h cut omega I. Substituting that values, you will get zeta as e raised to minus beta phi naught pi I equal to 1 to 3n e raised to minus half beta h cut omega I divided by 1 minus e raised to minus beta h cut omega I. Now take the logarithm. Log zeta is minus beta phi naught plus logarithm of a product is sum of logarithms. Okay, so this product will again be sum sigma I equal to 1 to 3n logarithm of e raised to minus half beta h cut omega I divided by 1 minus e raised to minus beta h cut omega I. Okay, now internal energy U is minus dou q by dou beta. Q is grand potential and it is minus dou by dou beta of log zeta. Okay, because grand potential is logarithm of grand partition function. So take dou by dou beta of this term with a negative sign. Then the first term will give you phi naught plus this term logarithm of log a by b is log a minus log b, and logarithm and exponential will cancel. This term will give you a minus half beta h cut omega I. Derivative with respect to beta will give you minus half h cut omega I, and there is already a negative here, so that will be simply half h cut omega I, and there is a summation also sigma I equal to 1 to 3n, and the last term will be log a by b is log a minus log b, so that will be minus sigma I equal to 1 to 3n dou by dou beta of log 1 minus e raised to minus beta h cut omega I raised to minus 1, because minus log a is log a raised to minus 1, minus log a is log a raised to minus 1. Okay, fine. This minus you can take this side and this becomes plus, and dou by dou beta of logarithm of this quantity. What is derivative of logarithm? 1 divided by that quantity 1 minus e raised to minus beta h cut omega I. Then take derivative of this quantity minus e raised to minus beta h cut omega I. Again the derivative is with respect to beta, so you will have a minus h cut omega I. This minus and this minus becomes plus, so this term becomes sigma I equal to 1 to 3n. H cut omega I is here. E raised to minus beta h cut omega I will go to the denominator, and 1 by e raised to minus beta h cut omega I becomes e raised to beta h cut omega I, and this becomes 1. Okay, when this term goes to the denominator, this divided by the exactly same time, that will give you 1. So you have a term inside curly bracket which is phi naught plus the 0 point energy of all oscillators plus temperature dependent term. Sigma I equal to 1 to 3n h cut omega I divided by e raised to beta h cut omega I minus 1. This is the total internal energy of a solid. Call this as equation number 7. Okay, the expression in curly bracket, this one, okay, the expression in curly bracket gives energy of solid at T equal to 0. That is a term which is independent of temperature. Okay, and in that phi naught is negative and modulus of phi naught is greater than the sum of all the 0 point energy. That means the term inside this curly bracket will be a negative term. Because phi naught is negative, these quantities are positive, but the magnitude of phi naught is greater than the sum of all these quantities. Therefore, the term inside curly bracket will be negative, and that is nothing but the binding energy of the lattice. Okay, that determines the binding energy of the lattice. That is why it is negative. And the last term in 7 represents the temperature dependent part of the energy, and which determines the specific heat of the solid. Because specific heat Cv is dou u by dou T at constant volume. When you take the derivative with respect to temperature of internal energy, you will get Cv. So the temperature dependent part in this equation, that is the last term, will give you the specific heat. When you take the derivative with respect to T, this h cut omega I is a constant that is independent of T, and 1 divided by e raised to beta h cut omega I minus 1. Beta is nothing but 1 by kt. So this contains temperature. So 1 by x derivative is minus 1 by x square. E raised to h cut omega I by kt derivative is e raised to h cut omega I by kt into derivative is with respect to t. So this will be minus h cut omega I by kt square, because 1 by t derivative is minus 1 by t square. Rearranging this, we can write it as Cv equal to k into sigma I equal to 1 to 3n h cut omega I by kt the whole square e raised to h cut omega I by kt divided by e raised to h cut omega I by kt minus 1 the whole square. This is equation number 8. Okay. Now, to find the exact value of Cv, we should know about the frequency spectrum. How the frequencies are varying between the oscillators. Among the 3n oscillators, how the frequencies are varying. Okay, with that knowledge only we can find the final value of Cv. We can obtain this frequency spectrum either through experiment or making certain plausible assumptions about it. We have two different approaches. First one is by Einstein and second one is by Debye. First we will discuss the Einstein approach. Einstein assumed that all frequencies are equal. All the 3n one-dimensional harmonic oscillators have the same frequency, and let it be omega e. Okay, Einstein frequency omega e. Then Cv becomes k into sigma h cut omega e by kt whole square e raised to h cut omega e by kt divided by e raised to h cut omega e by kt minus 1 the whole square. Okay, so all the omega i's replaced with the omega e. This summation is there. Okay, so there will be identical terms like this. There will be 3n identical terms. Okay, this summation, due to this summation there will be 3n such terms, sum of 3n terms. So that will give you a 3nk into h cut omega e by kt whole square e raised to h cut omega e by kt divided by e raised to h cut omega e by kt minus 1 the whole square. Okay, I will call these terms as e of x with x is equal to h cut omega e by kt. Okay, if you name this quantity h cut omega e by kt as x, then this quantity is nothing but x square e raised to x divided by e raised to x minus 1 whole square. That is known as e of x, Einstein function. And this x equal to h cut omega e by kt, we can write this as theta e by t, where theta e is a quantity which is having the dimension of temperature, and it is known as Einstein temperature. Einstein temperature. Okay. So Cv is 3nk into E of x. This is the plot of Cv by 3nk versus T by theta. Cv by 3nk, from that expression you have x square e raised to x by e raised to x minus 1 the whole square with x is equal to theta by t. But here in the x-axis you have t by theta. So make a variable change, let y equal to t by theta. So replace all the x with 1 by y. So this becomes e raised to 1 by y square e raised to 1 by y minus 1 the whole square. If you plot this function, it will be like this. Okay, this is the plot of this Cv by 3nk versus t by theta. So what are the inferences? At high temperatures, this is a plot given in Pathria's textbook, Cv by 3nk versus t by theta. This dotted line is the curve obtained by using Einstein assumptions or using this equation. This is this pink curve is exactly this dotted one. And this solid curve is the one obtained by Debye's approach that we will discuss later. And this t cube law also we will discuss later. So this dotted line is the one obtained by Einstein. At high temperatures, that is as t tends to infinity, you can see that this curve approaches a value 1. That is Cv by 3nk equal to 1 or Cv equal to 3nk. Cv equal to 3nk. And that is the classical result. Okay. From Dulong-Petit's law, we know that the specific heat opacity at constant volume for a solid is 3nk. It is constant, and that is the law by Dulong and Petit. The Cv is a constant and it is given by 3nk. For Einstein also, that result, he obtained the same result at a high temperature region. But at low temperatures, when t less than theta e, you can see that that is when x greater than 1. Okay, when x greater than 1, if this x value is very high, this minus 1 can be neglected. This e raised to x square becomes e raised to 2x. When it go to the numerator, that becomes e raised to minus x. Okay, e raised to x by e raised to 2x becomes e raised to minus x. That is, Cv falls exponentially fast. Cv falls exponentially fast and tend to 0 as t tends to 0. Okay, so using Einstein approach, we can say that as t tends to infinity, specific heat reaches a constant value 3nk. For low temperatures, specific heat falls exponentially and tend to 0. But the theoretical rate of fall obtained by Einstein is too fast compared to the observed rate. This is the observed rate. This dots actually represents the experimental result, and this fall is slow compared to Einstein's result. Okay, or Einstein's result gives decrease of Cv that is very fast compared to the experimental value. Okay, so that is one failure of Einstein's model. But Einstein's theory provides a theoretical basis for understanding the observed departure of Cv from the classical law of Dulong and Petit. Because according to Dulong and Petit, Cv is 3R per mole per degree and is independent of temperature. Okay, that is Dulong-Petit law. The specific heat of a solid is constant. It is independent of temperature. That is the law by Dulong and Petit. But experimentally it was observed that the specific heat opacity decreases as temperature decreases. Einstein's theory succeeded in explaining the decrease, but the rate of decrease was very fast. So Debye made a modification, and now we will discuss the Debye approach. The modification was frequency of oscillator is not constant for all the oscillators, but it can vary from 0 to a maximum value omega d continuously. Okay, the frequencies of oscillators can take any value between 0 and omega d. But since there are a total of 3n modes, there are only 3n modes. So when you integrate the number of modes, you should get 3n. Okay, this g of omega d omega is the number of modes having frequency in the range omega and omega plus d omega. When you integrate from 0 to omega d, you will get the total number of modes. That should be 3n. Okay, I think it is clear. Call this as equation number 12. Now, from the last lecture, we have this expression for density of or number of modes having frequency omega and omega plus d omega, density of states. G of omega d omega is equal to v omega square d omega divided by 2 pi square c cube. Okay, this expression we derived in the last lecture. You can refer lecture number 27. But there we multiplied with a 2 in order to account for the 2 transverse modes of vibration for the electromagnetic waves. Okay, but in this case we can have longitudinal modes also. Okay, so in the case of phonons, we have longitudinal modes as well as transverse modes. Let CL be the velocity of longitudinal mode and CT be the velocity of transverse mode. Then g of omega d omega can be written as v omega square d omega by 2 pi square CL cube corresponding to longitudinal mode plus 2 into this 2 accounts for the 2 different transverse modes, 2 different polarization states. So 2 into v omega square d omega divided by 2 pi square CT cube. This is the total density of states or number of normal modes in the frequency range omega and omega plus d omega. Call this as equation number 13. When you substitute the g of omega d omega value in this expression 12, you will get it as 0 to integral 0 to omega d v omega square by 2 pi square d omega into 1 by CL cube plus 2 by CT cube equal to 3n. So you can take all these quantities to the right hand side except this integral omega square d omega. All others are constant. Omega square d omega, when you integrate, you will get omega d cube by 3. So omega d cube by 3 equal to 6 pi square n by v into 1 by CL cube plus 2 by CT cube whole raised to minus 1. Therefore omega d cube equal to, this 3 will go to the right hand side, 18 pi square n by v 1 by CL cube plus 2 by CT cube whole raised to minus 1. This is equation number 14. So from here you can find the value of 1 by CL cube plus 2 by CT cube, and it is nothing but 18 pi square n by v omega d cube. Put this value in equation number 13. Okay, in equation number 13 for 1 by CL cube plus 2 by CT cube, substitute this value. Then you will get g of omega d omega equal to 9n by omega d cube into omega square d omega for omega less than or equal to omega d. And for omega greater than omega d, there are no normal modes, so the number will be 0. So g of omega d omega is 9n divided by omega d cube into omega square d omega for omega less than or equal to omega d, and 0 for omega greater than omega d. We can compare this result with an experimental result. So consider this graph, g of omega versus omega graph, and this is the normal mode frequency distribution g of omega for aluminium. This solid curve is derived from X-ray scattering measurements. So this is an experimental result, and the dashed curve represents the corresponding Debye approximation. In the case of Debye approximation, you can see that up to the cutoff frequency it varies as omega square, so it is a quadratic curve. Beyond omega d, it is 0. So this dotted line is parabolic up to omega d, then it is 0. But the experimental curve is something like this. For low frequency, Debye approximation is reasonable. For low frequency, the dotted line and solid curve are matching. But for high frequency, there are serious discrepancies. But for averaged quantities like specific heat capacity at constant volume CV, the finer details are not important. So for calculating quantities like CV, we can use Debye's approximation. Okay. And another fault is that we considered same cutoff frequency for both longitudinal and transverse modes. Actually, the longitudinal and transverse modes should have their own cutoff frequencies. And we can calculate that cutoff frequencies using these expressions. Among the 3n normal modes, n will be longitudinal and 2n will be transverse. So, integral 0 to omega dl, this L corresponds or denotes longitudinal cutoff frequency, omega dl, into g of omega d omega, that is v omega square divided by 2 pi square cl cube into d omega, that should be equal to n. There will be n longitudinal modes, and integral 0 to omega dt, transverse mode cutoff frequency, v omega square d omega by pi square ct cube. There is a factor of 2 multiplied by a factor of 2 when you compare it with the longitudinal mode, and that 2 corresponds to the two polarization states in the case of transverse mode that we will discuss, that we discussed in lecture number 27, and that should be equal to the 2n modes of transverse modes. Okay, so among the 3n normal modes in a solid, n are longitudinal, 2n are transverse. So solving this, you can find omega dl cube by 3 equal to 2 pi square n by v cl cube. Omega you can write it as 2 pi nu, where nu is frequency, 2 pi nu dl whole cube by 3 equal to 2 pi square n by v cl cube. But c divided by nu is nothing but lambda. So lambda cube is equal to, rearranging this, you will get 8 by 6 pi v by n, or lambda minimum. Okay, the maximum frequency corresponds to a minimum wavelength. Lambda minimum is equal to 4 by 3 pi v by n whole raised to 1 by 3. If you calculate the same quantity for transverse modes, you will get it as omega dt cube by 3 equal to 2 pi square n by v ct cube. Again omega dt is 2 pi nu dt whole cube by 3 equal to 2 pi square n by v ct cube, or lambda cube equal to 8 by 6 pi v by n, or lambda minimum equal to 4 pi v by 3n whole raised to 1 by 3. So for longitudinal as well as transverse modes, the minimum wavelength is exactly the same. Minimum wavelength is exactly the same, and it is of the order of interatomic distance. And it is of, here v is the volume and n is the number of particles. So this is of the order of interatomic distance. Okay, so the cutoff wavelength is comparable to the mean interatomic distance in the solid. And for a wave of atomic displacements, it is meaningless to speak of a wavelength shorter than interatomic distance. That is why this cutoff wavelength is like this. Lambda minimum equal to 4 pi v divided by 3n whole raised to 1 by 3. Okay. Now, we can calculate specific heat capacity using equation 8, that is Cv equal to K into sigma I equal to 1 to 3n h cut omega I by Kt whole square e raised to minus h cut plus h cut omega I by Kt divided by e raised to h cut omega I by Kt minus 1 the whole square. This is equation number 8 we already derived. Now, we can replace this summation with integration by including the density of states. So, this summation becomes integral 0 to omega d. G of omega d omega is nothing but 9n by omega d cube into omega square d omega. And these quantities are h cut omega by Kt whole square e raised to h cut omega by Kt divided by e raised to h cut omega by Kt minus 1 the whole square. There is no I because this omega is now a continuous variable. It can vary from 0 to a maximum value, that is cutoff frequency omega d. Up to that value, this g of omega d omega is 9n divided by omega d cube omega square d omega. Beyond omega d, this g of omega d omega becomes 0. Okay. So this is CV. Now put h cut omega by kt as x. Then d omega becomes kt by h cut dx. And when omega equal to omega d, this x becomes h cut omega d by kt and call it as x naught. If we make these substitutions, then you will get CV is equal to, here you have a 9 that will come outside, 9 nk divided by omega d cube into, you multiply and divide with an h cut by kt whole cube. So there is 1 by h cut by kt whole cube, and you will have here in the numerator an h cut by kt whole cube, and all other quantities are here. Omega square h cut omega by kt the whole square e raised to h cut omega by kt divided by e raised to h cut omega by kt minus 1 the whole square d omega. Okay, CV is equal to, from 9nk you can write it as 3nk into 3, and this omega d you can take into the this quantity, this h cut omega d by kt whole cube, you can call it as x naught cube. Integral 0 to omega d becomes integral 0 to x naught. Here you have an h cut cube by kt cube, but in d omega you will have a kt by h cut dx. So one of the h cut by kt will cancel, and this becomes h cut omega by kt the whole square. Here you have h cut omega by kt the whole square. Those will make it x raised to 4 e raised to x dx by e raised to x minus 1 the whole square. So this is 3v, and this quantity you can call it as d of x naught. Okay, d of x naught, Debye function. So CV is 3nk into d of x naught, where x naught is h cut omega d by kt, and h cut omega d by k you can denote it as Debye temperature, theta d by t. Okay, so theta d is a quantity having the dimension of temperature, and it is known as Debye temperature. Okay, d of x naught is Debye function is 3 by x naught cube integral 0 to x naught x raised to 4 e raised to x by e raised to x minus 1 the whole square dx. This is equation number 18. Value of x naught is theta d by t, it is equation number 19, and CV 3nk d of x naught, equation number 17. Okay, you can do an integration by part for this function by taking x raised to 4 as first function. So 3 by x naught cube is in the is outside. This first function is x raised to 4. Integral of second, so integral of e raised to x by e raised to x minus 1 the whole square dx, minus integral of derivative of first, x raised to 4 derivative is 4x cube into integral of second function. Okay, put u equal to e raised to x minus 1, then du becomes e raised to x dx. So this integral becomes integral du by u square. Here also you will have du by u square. What is integral du by u square? It is minus 1 by u. Okay, so you will get it as minus, you can incorporate in here. So that becomes x raised to 4 by 1 minus e raised to x instead of e raised to x minus 1. From 0 to x naught, this is the boundary term, plus here also you have a minus 1 by u, that minus and this minus becomes plus, integral 0 to x naught 4x cube divided by e raised to x minus 1 dx. So d of x naught you can write it as this term, and you put the upper limit, this becomes x naught raised to 4, that will cancel with this x naught cube, and there will be an x naught in the numerator, and denominator you can write it as e raised to x naught minus 1 by putting a negative sign here. So that becomes minus 3x naught divided by e raised to x naught minus 1 plus this 3 and this 4, when it multiplies it will get 12 by x naught cube integral 0 to x naught x cube dx by e raised to x minus 1. This is Debye function, and it is equation number 20. Now for t very much greater than theta d, that is for x naught very much less than 1. If x naught is very much less than 1, you can expand this like this, d of x naught equal to minus 3x naught e raised to x naught is 1 plus x naught by 1 factorial plus x naught square by 2 factorial plus etc. minus 1, this minus 1, whole raised to minus 1. This is in the denominator, so there is whole raised to minus 1 plus 12 divided by x naught cube, integral 0 to x naught, x cube is here, 1 by e raised to x minus 1 becomes 1 plus x by 1 factorial plus etc. minus 1 whole raised to minus 1 dx. Okay, so this quantity and this quantity are exactly the same. The difference is here it is x naught and here it is x. Okay, this 1 and this 1 will cancel. This 1 and this 1 will cancel. Here also this 1 and this 1 will cancel. You can take an x naught outside, but it will be 1 by x naught when it comes outside because there is a minus 1. So it will be minus 3 x naught by x naught. The first term you will have 1, the second term you will have x naught by 2 factorial, in the third term you will have x naught square by 3 factorial plus etc. whole raised to minus 1 plus 12 by x naught cube, integral 0 to x naught. Again you can take an x outside, but it will be 1 by x outside because there is a negative 1. So x cube by x, 1 plus x by 2 factorial plus x square by 3 factorial plus etc. whole raised to minus 1. Okay, d of x naught equal to, this x naught and x naught will cancel, minus 3. This I can write it as 1 plus a quantity whole raised to minus 1 plus 12 by x naught cube, integral 0 to x naught, x cube by x is x square. Again here you can write it as 1 plus a quantity whole raised to minus 1 dx. We have binomial expansion 1 plus x raised to n as 1 plus nx plus n into n minus 1 by 2 factorial x square plus etc. Applying that, you will get d of x naught is equal to minus 3. There is a minus 3 here. 1 plus, instead of x, you have quantity inside this bracket. So 1, n is minus 1. Instead of n, you have minus 1. So 1 minus that quantity inside bracket plus, why this plus? N is minus 1. So minus 1 into minus 2 divided by 2. That becomes plus 1. So plus that quantity square plus etc. Okay. Here you will have plus etc. plus this term 12 by x naught cube, integral 0 to x naught, x square. Remaining is again binomial expansion 1 minus that quantity inside bracket plus that quantity inside bracket square plus etc. into dx. So d of x naught equal to minus 3 into 1, it is minus 3. Minus 3 into x naught by 2, it is plus 3 x naught by 2, 2 factorial. And you will have a minus x naught square by 3 factorial, that is a minus x naught square by 6 here plus x naught square by 4 here, because this first term square, that will give you an x naught square by 4. So minus x naught square by 6 plus x naught square by 4, that will give you an x naught square by 12 multiplied with this minus 3, that will give you minus 3 x naught square by 12 plus higher order times. Plus this term 12 by x naught cube, integral 0 to x naught x square. This first term is 1. Then you will have a term x by 2 factorial. Then from here you will have a minus x square by 6. From here you will have an x square by 4. That will give you an x square by 12 plus higher order times. So d of x naught equal to minus 3 plus 3x naught by 2 minus 3 by 12 x naught square here. That becomes minus x naught square by 4 plus 12 by x naught cube into x square into 1. It is x square. X square dx integral is x cube by 3. Putting limits, you will get x naught cube by 3. X square into minus x, that is minus x cube by 2. When you take the integral, that becomes minus x naught raised to 4 by 8. Third term is x square into x square, x raised to 4 by 12. When you take the integral, it is x naught raised to 5 by 60 plus etc. So d of x naught is equal to, there is a minus 3 here and x naught cube and x naught cube will cancel. 12 by 3 becomes 4 plus 4 here minus 3 here. So you will get the first term as 1. Then 3x naught by 2 here. This term will be again minus 3x naught by 2. This x naught cube and x naught raised to 4 will cancel. 12 and 8 will cancel, 3 by 2. So it is minus 3 by 2 x naught. This is plus 3 by 2 x naught. That will cancel. Minus x naught square by 4. And here you will have a plus x naught square divided by 5. That will give minus x naught square by 20 and so on. Okay, so we will retain only we have to consider only first two terms. There will be higher order terms. This is equation number 21. Okay, now we will consider the different cases as t tends to infinity. Temperature tends to infinity. This x naught is actually x cut omega d by kt. T tends to infinity means x naught tends to 0. So d of x naught will be simply 1. So Cv becomes, Cv is actually 3 nk into d of x naught. So d of x naught tends to 1 means Cnk, Cv tends to 3 nk. Cv tends to 3 nk. Now for t very much less than theta d, that is x naught very much greater than 1, what happens to the value of d of x naught? This value of d of x naught is applicable only when x naught is very small. X naught is very small. Okay, that because for writing this binomial expansion and for neglecting the higher order terms, x should be very small. Okay, x should be very small. And for x very large, x naught very large, d of x naught should be, the first term is, what is d of x naught? This quantity. Here if x naught is very large, e of x naught minus 1 becomes e of x naught, e raised to x naught, and that will go to the numerator, and that is a term of the order of e raised to minus x naught, e raised to minus x naught. So you will have a term which is of the order of e raised to minus x naught, and the next term is 12 by x naught cube, integral 0 to x naught. X naught is very much greater than 1. So you can take it as integral 0 to infinity. If it is integral 0 to infinity, then this is a standard integral and the answer is pi raised to 4 by 50. So this is applicable only when x naught is very large. Then d of x naught is approximately 12 by x naught cube into pi raised to 4 by 50. Okay, because you can neglect this term also. Therefore, that is nearly 4 by 5 pi raised to 4 by x naught cube. And Cv is 3 nk d of x naught, that is 3 nk into d of x naught is 4 by 5 pi raised to 4 by x naught cube. X naught is nothing but theta d by t. Substituting that, you will get Cv as 464.4 t cube divided by theta d cube calorie per mole per Kelvin. This here, for obtaining this result, we substituted n as Avogadro number Na, and K Boltzmann constant, pi is a constant. Okay, theta d is Debye temperature. So substituting the values of these constants, you will get it as 464.4. So Cv, we can say that Cv is proportional to T cube. Cv is proportional to T cube. For low temperatures, specific heat capacity of a solid varies as third power of temperature. Cv proportional to T cube, that is T cube law. Okay, so from the measurements of low temperature specific heat of a solid, we can check the validity of T cube law. Okay, so if you can measure experimentally the low temperature specific heat of a solid, we can check the validity of T cube law. Also, we can obtain an empirical value for Debye temperature. Okay, from that we can find the value of Debye temperature also. Once we have Cv and T, we can calculate Debye temperature. Also, theta d can be calculated using this expression. Theta d is h cut omega d by t, where omega d, the cutoff frequency, we already have this expression. So using this expression also, we can calculate theta d. Now, once theta d, Debye temperature, is known, the whole temperature range can be covered theoretically by making use of the values of d of x naught. Because here we discussed only two special cases. One is t tends to infinity, the other one is t tends to 0. What about the in-between values? For calculating the in-between values, you have to calculate d of x naught. For calculating d of x naught, you have to find what is x naught. And what is x naught? X naught is theta d by t. So for substituting for x naught, we need the value of theta d. Okay, so once we have the value of theta d, we can cover theoretically the entire values of d of x naught. Okay, or we can plot CV for the entire temperature range. Okay, plot CV for the entire temperature range. Now, the low temperature results can be further confirmed by the plot of CV by T versus T square. This is actually an experimental plot. These dots represents the experimental values. A plot of CV by T versus T square for potassium chloride KCl, showing the validity of Debye's T cube law. Okay, CV by T versus T square means CV versus T cube, right? So CV by T versus T square, a graph is straight line, means CV will obey T cube law. Okay, and the experimental data points are all lying in the straight line. Okay, the experimental points are due to Keesom and Perlman, and this experiment was done in 1953. Okay, so if the specific heat measurements of a given system conform to T cube law, we can infer that thermal excitation in the system are accounted for solely by phonons. Here we are considering only the case of phonons, and we got a T cube law. That is, for low temperature, CV is proportional to T cube. So when you measure the specific heat values at low temperatures, and if it obeys the T cube law, then we can say that the thermal excitations in the system are accounted for solely by the excitation of phonons. Okay. Now, all these are developed for solids. Okay, till now we are talking about solids, but in the case of liquids also we can apply this theory with some modifications. So for liquids, what are the modifications? First one is, it cannot withstand shear stress. For liquids, when you apply a tangential force, it will flow. So it cannot withstand shear stress. So they cannot sustain transverse modes of vibration. There will be only longitudinal modes. So the total number of modes will be simply n. There will be only n longitudinal modes. That is the first difference. Second one is, vibration will not be strictly harmonic. Other type of excitations like vortex flow, turbulence, etc. may be there. Okay, we will consider one example. Helium is the only substance that remains liquid at temperature low enough to exhibit T cube behavior. This T cube behavior is exhibited at a very low temperature, and helium is the only substance that remains liquid at that temperature. Other substances will convert to solid, but helium is the only substance that remains liquid at very low temperature, that temperature low enough to exhibit T cube behavior. And if you are considering He4, we can use the theory of phonons. Whereas if you are considering He3, that is fermion, so we have to apply Fermi-Dirac statistics. But for He4, we can use the theory of phonons, that is Bose-Einstein, a particle which obey Bose-Einstein statistics. So from equation number 16, we have for the longitudinal mode, the cutoff frequency is like integral 0 to omega dl v omega square d omega by 2 pi square Cl cube equal to n. There are only n longitudinal modes of vibration. Solving this, you can take 2 pi square Cl cube to the right hand side, v to the right hand side. Then omega square d omega becomes omega cube dl by 3. That 3 will go to the right hand side and becomes 6 pi square n by v Cl cube. G of omega d omega, the density of states becomes v omega square d omega by 2 pi square Cl cube. Using these two expressions, you can write G of omega d omega in terms of cutoff frequency. That becomes 3n by omega d L cube into omega square d omega. And Cv, specific heat, is K into sigma I h cut omega I by kt whole square e raised to h cut omega I by kt divided by e raised to h cut omega I by kt minus 1 the whole square from equation number 8. You can replace this summation with integration with the density of states G of omega d omega. Substituting for G of omega d omega, you will get this. The only difference between the earlier expression for Cv and this expression is there was a 9, okay, because when we consider the case of solid, in the expression for Cv, here you have 9n, and in the case of liquid, it is 3n. Okay, so the only difference is a factor of 1 by 3, a factor of 1 by 3. So when you derive the equation for CV, the final expression at low temperature, that is equation number 23 in the case of solid, that will change to that expression for solid is actually 12 pi raised to 4 nk divided by 5 t by theta d whole cube. That will change to CV equal to 4 by 5 pi raised to 4 nk t by theta d whole cube. 12 becomes 4 because there is a variation of 1 by a factor of 1 by 3. Okay, so CV will be, for liquid, CV will be 4 by 5 pi raised to 4 nk t by theta d whole cube. What is theta d? It is h cut omega dt. Okay, not omega dt, this omega dl, longitudinal, divided by k, and omega dl is nothing but 6 pi square n by v raised to 1 by 3 into cl from here. Okay, from this expression. So substitute that values here, you will get CV as 4 by 5 pi raised to 4 nk t cube k cube by h cut cube into v divided by 6 pi square n cl cube, and that is nothing but 2 by 15 pi square k raised to 4 by h cut cube cl cube into vt cube. Now we can calculate the specific heat per unit mass of the liquid, So divide this equation by an m, and this v will go to the denominator. M by v is nothing but density. So you will get 2 by 15 pi square k raised to 4 by rho h cut cube cl cube into t cube. And for liquid helium, density is 0.1455 gram per cc, and the velocity of sound wave in liquid helium is 238 meter per second. Substituting that values here, you will get CV as 0.0209 T cube joule per gram per Kelvin. And the experimentally observed value is CV equal to 0.0204 plus or minus 0.0004 into T cube. So the theoretically obtained value and the experimentally observed value is in very good agreement. Okay, so this is again a further confirmation of the success of Debye theory. Okay, thank you.